In this video, I want to show you how to go from geometry to algebra to a program at the hand of an example, how to compute the greatest common divisor, the GCD, with Euclid's algorithm. So let's start with the geometry. So we draw two lengths, and maybe I call them N and M for reference. So this is N, and this is N. And now I'm interested in computing the greatest common divisor of N and M. So I'm looking for a length that fits both N and M. So let me draw this. It doesn't need to be like very precise because it's just to give you an idea. So I have to find a length that fits into M. And then also, when I continue, a multiple of this needs to fit into N. So to try this. And then also maybe like this. Okay, and so what we see here is that the blue block, which is the greatest common divisor, divides not only N and M, but also difference between N and M. That's what this picture is supposed to show. And this gives us an idea for an algorithm, because now when we want to know the greatest common divisor of N and M, we can also look at for the greatest common divisor of M and N minus M. So let's see how this plays out if we make a concrete example. So let's do the greatest common divisor of 42 and 30. So here. So this is 42 and the lower one is 30. Okay, so what the picture tells us is that we can compute this by looking instead for the greatest common divisor of 30 and 42 minus 30. So 32 and 12. And now we can keep on doing this, but let me use a different color for the next step. So I'm deleting 30 and 12 here and writing this in a different color, 30 and 12. And I now keep on doing the same, but with different inputs. Right? So now I keep computing the GCD, and I take the smaller number, and I take 30 minus 12 is 18. So actually, this is an example where now the second number becomes bigger than the first number. But that should not prevent us from continuing the computation. So let me just erase this again. I remember 12 and 8. And I rewrite the same numbers in a different color. 12 and 18. And so now the larger one is 18 and the smaller one is 12. And then I keep on doing this. So I do the GCD now of 12 and 18 by using two smaller lengths. So this is 12 and 18 minus 12, which is 6. And now we're closing in on the results. So what's a color I didn't use yet? So let's erase 12 and 6 and remember 12 and 6. So 12 and 6 in yet a different color. So now we have 12 and 6 here. And so n minus m is 12 minus 6, which is 6. So we get to the GCD of 6 and 6. And now the lengths are the same. So the result is just 6. So we see here how the geometry helps us. And that must be the way Euclid has done it, because he didn't have algebra at the time. But if we can write this down in algebra, we are really close to a program. So that's the point. So what does algebra mean? So algebra means that we find an equation written with variables that justifies all of these steps. Right? So that's what we want. So how can we write down an equation? So GCD of n and m. So I use variables names n and m now. And so the question is now how to find the equation that describes these computation steps. And if you look carefully, we see here that sometimes the first argument is bigger than the second argument, but also sometimes the first argument is smaller than the second argument. So it makes sense to have a case distinction here between these two cases. And also there's another case, which is that both of them are equal. So the first, we start with n is greater than m. The first argument is greater than the second argument. Then we have a case where the first argument is smaller than the second argument. And then we have a case where the first argument is the same as the second argument. So what happens in the, so now I'm here. So what happens here? So we compute the GCD of 42 and 30 by instead computing the GCD of 30 and 12. So 30 is the m in this example, right? So this is the second argument. And 12 is n minus m. Then n minus m. Okay, so now we're here in this case. So the first argument is smaller than the second argument. And so basically we write down the same thing, but we swap the letters n and m. So we do n and m minus n. And in the last case, we just return n itself. So now we're almost done. So this is a program. If you are programming in a functional programming language like Haskell, then this is almost a program. Maybe you just use some if then else for the case distinctions. So you can use if and then say if n is greater than m, then you do something, right? And because you have recursion, you can basically just write down the equation as it is above there. And then in the else case, because you have two more cases, you do another if then else. So I hope this illustrates that instead of going directly to the program, it pays to first think about the problem in the problems on the problem's own terms, that is geometry in our case. Then you think about how to translate the geometry to algebra, and then you think about how to translate the algebra into the program. Thanks for watching.